So let's talk about the force experienced by a charged object when it's in a magnetic field. So in the diagram on the right here, I have drawn Q, plus Q for a positive charge, and it's traveling at some velocity v. If we introduce a magnetic field, which is here, and that magnetic field is going to be, in this case, out of the page, and it's everywhere. I've only drawn the one notation of the field, but I'm saying it's everywhere so that I don't have to draw lots of them. So what's going to happen? Well, we can explore this experimentally and look at the results. So if we want to know what happens to the force on that charged object by a magnetic field, well, let's change the charge on that object. What we find is if you make the charge bigger, you get a bigger force on it. Now what else can we change to see the impact on the force? Well, we can change the magnetic field. And so it turns out if you have a larger magnetic field, you will end up with a larger force on that object. So as the magnetic field goes up, the force on the charged object goes up. Now there's one more thing that turns out to be very important, and that is the velocity. If there is no velocity, if the charged object is at rest, there's no force. So you can put a stationary charged object in a magnetic field, it does not experience a force. But as you introduce a velocity, you get a force, and that force is proportional to that velocity. The faster the object goes, the more the force will be experienced. And so if we bring all this together into an equation, we see that the force is equal to Q, the charge, and then the cross product of the velocity and the magnetic field. So there's a couple of things we want to tease out of this equation. The cross product, first of all, means that the result is a vector that is perpendicular to both of these vectors. So if we look at our example where we've got the plus Q here on the top right, and we have a velocity in that direction, we have a magnetic field that is out of the page. If in this case we were to apply the right-hand rule, we were to put our fingers, let's say, in the direction of the velocity, and then curl them upwards towards the magnetic field direction, we end up getting a force, and that force is going to be in this direction. So it's experiencing a force in that direction, and what that is going to accomplish is, because it is at 90 degrees to the current velocity, it's not going to speed it up, but it is going to change its direction, and that direction is going to be steadily changed such that it travels now in a circle, and that circle can be described in terms of its radius. So this force, which is caused by the magnetic field on the charged object, cannot change the charged object's speed. And because it cannot change its speed, it also doesn't change its kinetic energy. Only the direction changes. Now there is an important subtlety to recognize here. So if we want to look at this equation here, well, we can recognize that the magnitude of this force is going to be equal to Q V B sine of whatever angle is between those vectors. That's coming out of cross product. Well, let's recognize that if the angle is 0, then the force is 0. And if the angle is 90, then the force is maximum. And in that case, we wouldn't need that sine term at all, because sine of 90 is 1. Okay, one more important point here, and that is when we're applying this right-hand rule to a cross product, we get a direction. However, in this case, that direction is then multiplied by the charge value. And so if that charge value is negative, then we're going to have to flip the direction of the resulting force. So in this case, if this had been not a plus Q but a negative Q, the force would be in the opposite direction. Okay, so let's now consider what the radius of that motion would be. All right, so we know that in this case the force is 90 degrees from the velocity and 90 degrees from the and that's providing this circular motion. So we're going to have a force that is equal to our Q VB sine the angle, but in this case the angle between velocity and the magnetic field is 90, so that's just 1. And then because we've got the velocity and the force are at 90 degrees, it's providing the centripetal force. It's keeping this circular motion. And so that means that this is providing the mv squared over r, which is our centripetal force. So there we can now rearrange for our r value. So there we have an equation for the radius of this motion if we have the mass, velocity, charge, and magnetic field strength. Okay, so let's do an example where we have a proton, and this proton is going to enter some field where there's a 1 Tesla magnetic field. We already know the mass and the charge of a proton, so most of these values we know. We know the mass, we know the charge, we were told the magnetic field, but we don't know the velocity. But what does it tell us instead? Well, in this case it's saying, well, a 1 mega electron volt proton enters this magnetic field. And what is the radius of the resulting motion? Well, 1 MeV is a measure of energy. So we're being given a way to extract the velocity from the energy. But we're going to have to convert from mega electron volts into something that's easier to work with for this question. So we can say, well, our energy is relatable to charge and potential. This is where our definition for electron volts ultimately comes from. And what this is equal to here is the charge is E, because it's a proton, and this is 10 to the 6 volts. And so this we could then turn into an amount of energy, 1.6 times 10 to the negative 13 joules. That's the amount of energy that is carried by this proton. Now the amount of energy is also going to be 1/2 mv squared. And we can isolate the velocity, which is what we want. And the velocity is going to be equal to 2e over m square root. Now if we wanted to, we could also have just said, well, that's also equal to the square root of 2qv over m. However you want to do it, you end up with your velocity value of 1.4 times 10 to the 7 meters per second. And now that we have the velocity, we can go back up to our equation and we can find the radius. So this is the mass of a proton. This is the velocity that we just found, so we can just substitute in our values. And if we do that, we get a radius of 0.15 meters, or 15 centimeters. All right, so that's not so bad. The trick here was to be able to extract out the velocity from our energy of the proton. Now, it may be interesting to recognize that this is a very powerful technique for controlling the trajectory of a charged object with a magnetic field. And this has a great deal of applications. So let's just imagine that we have a beam of electrons. So we've got a beam of electrons and you want to be able to control their trajectory, and you know that you can do this with a magnetic field. So what are our options? Well, we could decide to have, let's pick blue, and we could say, well, let's put a magnetic field that is into the page. And if we do that, then, okay, let's think about the cross product here, which we're going to go velocity cross. My fingers are in the velocity direction, and then my fingers are going to curl into the screen, and I will get a resulting force that is upwards. That's the result of the cross product. However, remember that the force equation there had that Q term. And that Q term in this case is negative. So in this case, we're going to flip the direction of that force. And so there's going to be a downwards force. And so our trajectory here is going to be curving this direction. So not a very steady curve. In reality, this would probably work out very steadily. So we'll leave it kind of like that. Okay, so what about if we had a opposite direction? Let's maybe use green. So we could say, well, or what if we had a magnetic field everywhere that was, instead of into the page, out of the page? Well, in that case, we get a force in the opposite direction, and we would get a curve in this direction. So we can control the trajectory of an electron or a proton or any charged object using magnetic fields. And that's extremely powerful. One of the things that we can do with this equation and this ability, and I just want to make a note of this so that it's in the note. So just off to the side here maybe. So for the direction, of the force, must remember to consider the sign. Of Q. In our equation. So the force for an electron is the opposite direction than the right-hand rule. Okay. Now we can apply this to a couple of things. The first I'm going to point out is kind of neat, which is that, well, let's say we can create a beam of electrons, which we can do in a lab. We do. And so in this case, this is just a device that we have in the lab. And in this device, give me something that shows up. We have something that creates an electron beam. So this here is an electron gun. And it works through very similar principles to what we discussed when looking at the acceleration of charged particles in an electric field. So we can create an electron beam here, and then they're going to shoot out the bottom. And so once we do that, we can use the current that is flowing through these coils. So there's going to be a current in these coils. All these wires wrapping up are going to produce a magnetic field. So there's going to be a magnetic field. And that magnetic field is going to curve that electron beam in a circle. And you can see the electron beam in this case because this is a chamber where we have a low density gas that is taking a small amount of the energy of the beam and re-emitting it as light. So we have a tracer for this electron beam. And so what we can do is we can actually, because we can see what's going on visibly, we can actually measure what the radius is. So we can say, well, technically there's a scale in here for the diameter. But what we're thinking about here is we've got this radius. And so this radius is something that we can measure directly. The current is something that we can measure very directly because we're controlling that, and that produces the magnetic field. So what we use this for is to actually calculate experimentally the ratio of the electron charge to its mass. And we do that directly using the equation that we just talked about. So let's steal this equation again and think about how it can be applied here. And this is the way that fundamental properties of electrons were initially derived. We can rearrange this so that we get Q over M is equal to V over RB. And the velocity we can determine because of how we produce the electron stream. the radius we measure, the magnetic field we know because we know the current, and we can calculate that. And so this is how we got the ratio of the electron charge to mass originally. And that meant that if we could come up with an experiment to get one of those other values, we'd know the other. And what we ended up doing is there was an experiment that determined the Q, and from that then we had a measurement of the mass of the electron, and that's extraordinarily small. That's 9.1 times 10 to the negative 31 kilograms. So it's extraordinary that we could come up with a very good measurement of something so small. This also illustrates our ability to control the trajectory of particle beams using magnetic fields. Okay, one more application, and that's a cyclotron. So a cyclotron, we're going to do something very similar to what we just did here, but we're going to do this with a slightly different purpose. And so what's happening in the case of a cyclotron is that we have some, we're going to zoom in here and talk about what's going on. We're going to have some proton source. For example, it could be something else. But I'm going to say we have some proton source. Alright, so we have a proton source, and it's going to have some initial velocity. So it's going to send out a proton at some velocity, and it's going to enter an area where we have a magnetic field. So what should I use for the magnetic field? What did I use up here? We don't want that color. I'm just going to use brown. So we're going to have a magnetic field everywhere. And that magnetic field is going to be such that this is going to have a bent trajectory. Right? It's going to have a curved trajectory like this due to the magnetic field. And then what's going to happen, I've widely exaggerated the gap size here just for illustrative purposes. And across this gap, we're going to produce a potential difference across this distance. So across here, we're going to have a potential difference. And what that's going to do is that's going to accelerate. There's still going to be a curved trajectory, but I'm drawing it straight for illustrative purposes. So the speed will increase. And so what happens when the speed increases? Well, when it's got a higher velocity, our radius is going to be bigger. Okay, so that means that it's going to curve around a larger curve, and then it's going to re-enter this potential difference. Now, if that was the same, it would actually then slow it down. So what we're going to have to do is we're going to have to flip this. So we're going to have to flip our potential difference for each crossing. So then, just to illustrate here what's happening, we're going to have again a speed increase, and then it's going to be going even faster, and so then it's going to go over a larger curve, and then it's going to again accelerate. And you see what's happening. You have these periods of acceleration across this same gap, and then it's spiraling larger and larger and larger. Of course, all of this is a bit exaggerated for illustrative purposes, but this could actually happen. That was really bad. I'm going to do a slightly better job, please. And so what you're able to do is accelerate a particle in a very compact way, very efficient way. So you're able to get a huge acceleration in a reasonably sized space. So this is a very efficient way to create a beam that is a high energy or high velocity beam. And eventually, of course, it's going to exit. And usually this is, very purposeful. So we're going to have an exit point. So this is going to be some high energy, high velocity particle beam. And so this could have a variety of purposes. This could be for an experimental physics experiment. It could be for proton beam therapy to treat a cancer tumor. It could be, and often, these are used for this, you're bombarding a substance to change its structure, so it's a radioactive nucleotide that's used for tracing of different bodily functions. So you've got an organ function you want to trace out, or you want to trace some structure. You can use a radioisotope to do that, and this is typically how we produce those substances. So you could have some target here. Okay, so that is our introduction to the force provided by a magnetic field on charged particles. We have an equation. We've got to be a little careful in assigning direction depending on the charge, but it's extremely useful, has all these applications, and I think that's good to practice and know about. That's it for now.